Okay, so take a look at this question here. We have 2 moles of diatomic I2 vapor, and it gives them some information about it, the atomic mass units for the gas, and then 200 degrees C in a large cylinder. Gives you the pressure of the cylinder, and is pressured by means of a piston. And the question is about the how much heat is needed to raise the temperature to 400 degrees C. And no more information is given. You are to assume that due to the high temperature and size of the mass, all molecular modes are active. No modes are frozen out. So what that means is, I'm guessing, is if you look at the heat capacity here versus temperature, there are modes that are added at increasing temperatures, and the most modes that you can have are 7 halves R. Normally with a diatomic molecule you're looking at 5 halves R, unless you're above 600 degrees C, and then if it's a monatomic molecule you're looking at 3 halves R. That's supposed to be 3 halves R. So how much heat is added to make this transition happen? So let's see. Let's draw a picture here. We've got a fixed cylinder, and the cylinder is being held in there by a piston, and the pressure is 2 atmospheres. 2 atmospheres, and let's see. It's I2. All modes are active, therefore the heat capacity at constant volume is equal to 7 halves times the R value, the gas constant. Okay, so let's go ahead and figure this out. The heat capacity at constant volume is equal to the change in heat per change in temperature at constant volume. So we have 2 moles of this. And what we're looking for in this problem is we're looking for how much heat is required. We know that the delta T is equal to 400 degrees C minus 200 degrees C. So a delta T is equal to 200 degrees C. Okay, let's just go ahead and attempt to solve this problem. There's not enough room here, so I'm going to pull up another sheet here. Okay, so I'll rewrite some of the things that we've been working with here. So we have that the heat capacity at constant volume is equal to 7 halves R, and R is equal to, I'm going to have to look this up, I don't even know what it is. Okay, I looked it up. It's 8.31 joules per mole Kelvin. Okay, so we have the change in heat per change in temperature is equal to 7 halves times 8.31 joules per mole Kelvin. Now we also know that we're dealing with 2 moles. Now, to be honest with you, I didn't know if this was a molar value or not. I'm discerning that based on the fact that moles shows up here. So we have 2 moles of this. And if we want to know what delta H is, we're going to need to multiply both sides by the delta T. So we get that the delta H is equal to 7 halves times 8.31 joules per mole Kelvin times 2 moles times 200 degrees C, which is the same thing. That's equivalent to 200 Kelvin. So I could actually place 200 Kelvin in here instead. Maybe that's what I should do. 200 degrees C, I will say 200 Kelvin. Let me just erase that. 200 Kelvin. And now let's watch the units. We have Kelvin here, we have moles here that cross out, and so we should get joules on the top here. So how much heat is required? We're trying to calculate that. So delta H, so 2 here times 2 here, that cancels. 7 times 200 is 1400 times 8.3. Let's see, I'm going to go, that to me, I'm going to do this in a very slow way. 8. Oh, I guess I'll just do it out. I'm going to, should I limit the 0.3? That's within 10% of Pete's number. So I'm going to say 8 times 0, 0, 0. 8 times 4 is 32. Carry the 3. 3, 8, 11. Roughly 11,200 joules. And this is plus or minus 10%. This is within Pete's limit of error for doing the calculations. It takes roughly 11,200 joules to raise the temperature up to 400 degrees.